Thank you for taking your time for my session, Productionizing ML with ML Ops and Cloud AI. I'm Kaz, I'm developer advocate from Google Cloud. So I will discuss these topics. What is ML Ops and how you can build a scalable ML development environment. And then I will discuss what are the gaps between the POC and production systems and how to fill them. And lastly, I will discuss how you can establish the practice of machine learning lifecycle management. So what is ML Ops? And I remember I started discussing this topic like 3 years ago. The first time was the session at Cloud Next San Francisco. And I wanted to start discussing about this topic because I learned so much from uh, software engineer / data scientist inside Google, and who has been operating the one of the largest machine learning production system at Google for like 12 or 13 years. And he said the launching the machine learning system is the easiest part. The hardest part is keep operating that system for many years because the real problems with the ML system will be found while you are continuously operating it for the long term. So we felt that the practices we have learned with the DevOps area can be also applied to building a machine learning production system and operating that. The DevOps is all about unifying the dev and ops for the software construction by using the automation and monitoring. And so this is not an talk only about the ops, but also a dev. In the area of the machine learning and AI, it should be a data scientist or researcher. So ops team and data scientists and other stakeholders and the different roles should be work together to build an DevOps infrastructure for the machine learning. That is the definition of the ML ops. It's all about unifying the development of the machine learning system and the operation system for the machine learning by utilizing the automation and monitoring. And there are two important publications from Google that I have learned so much. One is the machine learning, the high interest credit card of technical debt. This is written by the software engineering team that has been building and operating one of the largest production machine learning system in Google for many years. And they have learned a lot and put them many practices and learnings into this publication. Another one is the rules of machine learning, best practices for ML engineering. So with those important publications, I picked up a couple of the important rules or practices, and I'll be featuring some of them, and how to solve the problems by using the tools from Cloud AI. First, I'd like to discuss how you can build a scalable machine learning development environment. Because I have seen this pattern, anti-pattern in many cases in the past, depending on the ML superhero. So ML superhero can be an ML researcher, and also they can be a data engineer who can work with Apache Spark or BigQuery Redshift to work with the data warehouse or storage and do the large-scale data preprocessing. And also they can be an infra engineer because they can write a Python or Go or Java code. So they can even build the production system by themselves. And also can be a product manager, defining what's the requirement and what's the benefit of the product. And they can explain that clearly to the executives and stakeholders in the organizations. And they do this from POC to production. So the ML superhero is a great person, but it doesn't scale because even in the large enterprises, there could be only a couple of ML superheroes in a single organization. So if the enterprise want to adopt the machine learning and the AI into the multiple projects, like 5 or 50 or 500 different projects, depending on ML superhero, anti-pattern doesn't scale. Instead, you have to build a scalable ML AI team with the multiple roles, like data engineers, data scientists, ML engineer, and so on. And they have to work together so that we can split the responsibility into the multiple roles. For example, data engineer should be responsible for ingesting the data and apply the large-scale data preprocessing by using the BigQuery or Apache Spark and so on. Whereas the data scientist can focus only on designing the machine learning model, and also how to think about how they can achieve the high accuracy, or maybe can think about the explainability if needed. And also, the ops engineer can be responsible for building a large-scale continuous training pipeline, ML pipeline, and also testing, analyze, and validation of the behavior of the model, and the large-scale serving infrastructure, where you can deploy the model and run the prediction services at scale. So let's think about one scenario where our data scientist is visiting a cubicle of the ops team for asking to bring his POC notebook into the production system. So there's one anti-pattern you may want to avoid at this phase. This is a black box and the pattern. This is not the black box problem you are having with the deep learning model. Instead, it means it can be any kind of machine learning models can be a black box where the researchers and the engineers are not sharing the same knowledge in the same project. For example, researchers would create a prototype and pass it to the ops engineer. And then the ops engineer takes that and build an infrastructure with that. And without any close the collaboration between the researchers and the ops engineers, it's possible that the researcher would not understand what's happening inside the serving production system, whereas the ops engineer would not understand anything that is happening inside the machine learning model. This is the black box pattern you may want to avoid. Instead, at Google, a hybrid research approach where the engineers and the researchers are embedded together on the same teams. This helps to reduce the source of the friction significantly. So every time you build a team, you should not separate the researchers and the ops engineers. Instead, you have to build a scalable unit or team that shares the same the notebooks or the infrastructure, and they share the same knowledges. So the ops engineer have to think, what would be the best platform to do this? The machine learning platform that could be easily shared with both data scientists and ops teams. In the past or early days of the data scientists, usually the data scientists themselves would spend their times on homebrewing the development environment by purchasing the GPU machines and installing CUDA drivers, TensorFlow, everything, and building these software stacks by themselves. But if you want to scaling out the operation or adoption of machine learning in enterprises, you have to ask the professionals, like the ops engineers or technicians, to prepare for the development environment. And that should be shared with the data scientists and ops engineers so that they can easily bring the outcomes, the notebooks or POC result to the production system. So the one tool you can introduce here is the cloud services. So we have introduced multiple components in the cloud AI platform, such as the data labeling service or deep learning virtual machine images, AI platform notebook, which is a managed version of the Jupyter Notebook on Google Cloud, or Kubeflow pipeline, and training and predictions. So those are all designed as a shareable and a scalable machine learning development and deployment and serving environment. And those components can be easily integrated with the other cloud AI, Google Cloud products, such as Google BigQuery, Cloud Dataflow, Cloud Data Prep, Dataproc, Data Studio, and so on. And also another important product I want to introduce here is the TensorFlow Enterprise, which is a commercial version of the TensorFlow. So TensorFlow is an open source tool, but the TensorFlow Enterprise is a commercial tool provided from the Google Cloud. So that it's the best product for bringing your TensorFlow code into the production systems. So let's think about some other scenarios to learn what's the benefit of using TensorFlow Enterprise and the AI platform. For example, the data scientist would be asking the ops team to get the development of the PC with GPUs, with everything installed, like CUDA drivers, the TensorFlow, everything's installed. And he wanted what he wanted it delivered by noon because he had to finish his large-scale training job maybe in a couple of days. But ops engineer, it's really hard to handle that kind of request coming from the multiple data scientists because there are many the challenges the ops team would face. For example, the GPU machine is expensive and it takes so long time to purchase that. And also, in the past, in many cases, software stacks is managed by the data scientists themselves. So there'll be many different versions of the CUDA drivers installed, different versions of the TensorFlow installed, NumPy, Matplotlib, Jupyter, and so on. They are kind of the homebrew development environment. And also another problem is the over-provisioning of GPU resource. So one data scientist would need the 8 GPUs, like A100 GPUs right now to finish their training job right now. But other data scientists would forget about their GPU servers because their project has finished and they launched the product a while ago. So this is the over-provisioning problem. And so data scientists would not be able to get the professional technical support from technicians because those are all homebrew environment. Instead, you have to standardize everything. For example, you can introduce the deep learning VM or DLVM of TensorFlow Enterprise. This is a standardized software stack with the other virtual machine images. So if you create a virtual machine instance with this DLVM image, you'd have everything inside it pre-installed, starting from the CUDA drivers, NumPy, scikit-learn, and Jupyter, and TensorFlow 1.15, 2.1, or 2.3. I remember it was like 3 years ago when I tried to install everything by myself. I installed the latest CUDA drivers and installed the latest TensorFlow, and then I found at that time the latest TensorFlow version wasn't compatible with the latest CUDA drivers. So you had to install the CUDA drivers with the previous version. So that has been the major problem for the data scientist. Before starting the data science work, you have to spend like a half a day or maybe whole day just for installing and solve the incompatibility issues between these softwares. So instead, now you have the standardized software stack provided from Google, and you can create any instances like a compute engine instance or AI platform notebook instance with the standardized software stack. Also, you can get the benefits from the cloud environment. For example, you can use preemptible GPUs instead of the standard GPU instances. Preemptible GPUs means that they are the GPUs with lower priority. So it's possible while you are using the preemptible GPUs for a day, it's possible that that GPU instance can be abruptly automatically shut down a couple of times in a day. So it's not so useful for interactive use cases like using the Jupyter notebook on it. But if you are training a large like a CNN image training job, then this could be a great solution because the cost of the preemptible GPU is almost one third of the standard GPUs. So if it's just a training batch job with the checkpoints saved periodically, you can use the preemptible GPU at the one third of the standard GPU cost. And also you can get the benefits from the tensor processing unit or TPUs. That is the AI processor designed by Google. Let's take a look at some video to learn how you can get started with the deep learning VM. You can go to the console of the compute engine and create a new virtual machine instance and go to the marketplace to find the deep learning VM and click it. So that you can specify the deep learning virtual machines images and specify the number of the CPUs and the GPUs you want to use. And you can specify the versions of the framework like TensorFlow Enterprise and so on. And click the deploy button. So you can wait a couple of minutes to get the clear and new instance with everything installed. So you can do the many times of the build and scratch cycles. Build and scratch cycle. Build it and try it, and it doesn't work well. You can remove it and build the new instance from scratch instead. Another product I can introduce here is the AI platform training. This is a managed service for the training infrastructure, for the training service. And again, the AI platform training contains the standardized software stack for the data scientists, so you don't have to install everything from scratch. And also, the benefit you would get with the training is the distributed training environment. In the past, if you want to use like a multiple nodes of GPU servers, like 5 GPU nodes or 10 GPU nodes or maybe 50 GPU nodes for the large scale training, then you have to have another set of skill for building a distributed cluster of GPU instances, or maybe you have to hire the ops engineer for keep building and operating the large scale GPU cluster. This is just like the building and operating the Hadoop cluster in the past. So it takes so long time and cost, but this is an AI platform training is a managed service, so you don't have to spend much time. You can just press a couple of the buttons and then specify some configurations on the GUI and start the training, initiate the training so that you can easily access the power of the distributed GPU training GPU environment. Also, it provides the state-of-the-art and automated hyperparameter tuner that has been used by the internal Google projects for building the production Google machine learning models in many years. So you can get all the benefits that Google software engineers has been using for many years. So that was the topics for the development environment, or maybe how to get started with the productionizing this data science. And let's talk about what are the gap between the POC systems and production system, and how to fill those gaps. For example, one problem you'll be facing with the production is the portability and scalability. For example, the data scientist is asking the ops engineer whether the POC code on the Jupyter notebook can support 10 million users. Maybe it's possible, but the ops engineer have to do many things, have to add many capabilities to support the 10 million users and make everything's production ready. Because there are many gaps between them. For example, many POC notebooks can be locally dependent and also dependent on a certain person. So you always have to ask some data scientist to get through all the scripts written on the notebook, and that doesn't work for the production. In production, everything should be portable and shareable, and also you cannot rely on a single notebook instance. Everything should be scaling out, can be scaling out or scaling in with the auto scaling feature, and also you have to have the load balancers that can dispatch the incoming prediction request into the multiple instances or pods in the container environments. And also, you cannot be relying on the fragile manual process. You have to make everything reproducible from end to end. And also, you have to think about continuous monitoring and alerting, because you cannot have the data scientists keep watching the production system for 24 hours for 365 days. This is a responsibility for the ops team, and the ops team have to think about the monitoring and alerting, whether your machine learning model is making a benefit or profit for your businesses by watching out those metrics and KPIs. So there's another product I want to introduce here that is an AI platform prediction. This is another managed service for online or batch prediction, and it supports the auto scaling based on its traffic. And everything can be logged into the BigQuery, so the ops team can easily set up and continuous monitoring and alerting. And everything runs on the GK Google Kubernetes engine. And that supports the NVIDIA T4 GPUs for the better cost performance for the prediction workload. So let's look at how the data engineer or researcher can share on the same notebook with the ops engineer to bring the POC machine learning model into the production smoothly. So you can start with the usual Jupyter notebook environment. In case of the cloud AI, you can use the AI platform notebook that is a managed version of the Jupyter notebook, so that you can easily execute the SQL on BigQuery to download the training data from BigQuery, and use the pandas data frame to apply some pre-processing against that. And in this case, it uses the scikit-learn for defining and building the usual scikit-learn the training pipeline. And you can call the fit function to train the model. So far, this is the usual data scientist tasks by the researchers. But and you can use some the prediction methods for evaluating the result of the machine learning model. And then you can share the same notebook with the data scientist. Ops engineer. So the ops engineer can upload the model to the Google Cloud storage to register the model to the AI platform prediction for larger scale for serving. Now the model is up and running with the AI platform prediction that can take like millions of the requests per second with the multiple instances and with the higher availability. So within a single notebook, you can share that with the data scientist and the ops engineer and make a seamless pipeline from the data science, the POC to the ops engineer's production system. Another product I can introduce here is deep learning container. Again, this is the same software, a standardized software stack, same as the deep learning VM. But the difference is that this is a container image. So that, for example, the data scientist would be working with the deep learning VM, running with the notebook, and they would create their POC notebook on that. Then ops team can take that notebooks and easily porting it, migrating it to the container environment, because they share exactly the same software stack with the same versions. It's much easier to port everything into the container, so that you can run that container onto the multiple container environment, like AI platform training and prediction, and also you can use the Google Kubernetes engine, GKE, so that now everything is production ready. Because with those container environment, you can get those benefits of the container environment automatically, like scheduling of each instances. In the area of the container technology, they call it as pod. The one pod represents the single worker on a multi VMs. So you would have the multiple pods running inside each VM, and you would have the multiple VMs. And it takes so long cost on time, so long time, and it takes so much high cost. If you want to build everything, this kind of the scalable, the available setup from scratch and writing everything by yourself, instead, you can just start using the GKE or AI platform prediction to get all of these the benefits of the production container environment. Scheduling, lifecycle management, or scaling out the auto scaling, or load balancing of the incoming traffic into the multiple pod, logging and monitoring, troubleshooting, and security management, so that you can design the system's architecture like this one. So in this case, you are combining the multiple the products from Google Cloud to build the production scale training and serving infrastructure. For example, you can use the products like Cloud Data Flow or BigQuery for extracting the data, apply pre-processing with those data warehouses at scale. And then use the training data with the AI platform training for the larger scale training job. And then you can pass the model to the Google Cloud storage and use it with the AI platform prediction. And everything you are seeing on this slide is scalable and production ready. So by using those components on Google Cloud, you can automatically build the scalable production ready environment for both development and deployment, training and serving. And also there should be the performance issue. The data scientist tends to not spending so much time on optimizing performance while they are doing the POC phases, but ops team have to be responsible for getting the highest performance. For example, the data ingestion, ETL, or pre-processing for continuous training. So if you are using the TensorFlow Enterprise, you would automatically get the benefits of the optimized I/O performance for the Google Cloud Storage and BigQuery Reader. But you don't have to change the existing TensorFlow code so much. The data scientists can keep using the existing the dataset API. This is the standard API for reading the training data from the storage. But the difference is that you can specify the URI of Google Cloud Storage bucket, like gs:// bucket name and dataset name, so that the TensorFlow Enterprise binary can detect that and tries to get the higher the input performance by using the multiple thread and parallelizing everything. And you can do the same thing with the BigQuery by using the BigQuery Reader and BigQuery Client API. So the reading the results set from the BigQuery can be automatically optimized to get the higher performance. So this is the comparison graph between the previous version of the TensorFlow and the TensorFlow Enterprise version. You are seeing the almost doubled performance. That means you can pump much more data, training data into GPUs. So even if you are using the same P100 GPU, single GPUs, you are seeing this 30% increase on the GPU utilization rate just by using the TensorFlow Enterprise. And also you can get the technical support. Because the TensorFlow Enterprise is a commercial product from Google Cloud, you can open a new ticket with the standard the Google Cloud technical support program. And we can provide the up to 3 years of the technical support for each version of TensorFlow Enterprise. Lastly, I'd like to introduce the lifecycle management. Because in the past, it has been so tedious task for the data scientist for make everything reproducible. Instead, everything is, because it has been kind of a research project, those pipelines like ingesting data, data preparation, and everything could be easily fragile, and it has been so hard to make it everything reproducible. But if it's a production system, everything should be reproducible. Otherwise, the data scientist would get the emergency call from director and for asking for retraining the model that has designed like 3 years ago as ASAP, as soon as possible, because the customer is making a complaining about the dropped down the accuracy on the suggestion or recommendation the models. And also you have to aware of that. You have to be aware of that instead of the consumers notice that. So you have to you have to set up the continuous monitoring and alerting system. So those are the reasons why we have built a product called AI Platform Pipelines. This is a new platform for building an orchestrated pipeline just by combining the different bricks from the Lego bricks. Inside the AI platform, we use the Google Kubernetes engine as a runtime, and we use the Kubeflow pipelines, open source softwares for building those pipelines with the metadata store. So let's take a look at how it works. This video. If you go to the console of the AI platform pipeline, you would see in the DAG the data flow like this one. By clicking each block, you can watch what is happening in each phases of the ML pipeline, right? Like what is happening in my ingesting ETL job and what is happening with my training job and so on. And everything is managed as artifacts, like different versions of dataset, pre-processed dataset, or different versions of the trained models and hyperparameters. Those are all called the artifacts. And you can track all the lineage between the artifacts by using the lineage explorer. So everything should be reproducible. If you are getting a really great result with a certain experiment with the training, then you can track what is the exact version of the dataset to produce this model, and what is the hyperparameter, what is the design versions of the ML model design. So everything can be tracked and reproducible. So those are the topics I wanted to cover. So at first, I discussed what is ML ops and how to build the machine learning development environment, and how to fill the gap between POC and production, and how to establish the machine learning lifecycle management practice. That's it.